Hello everyone. This lecture we will talk about the combinations of a set and start with permutation of multisets. So first, let's define what is combinations of sets. Given a set S with cardinality n, and for integer k between 0 and n, by k combinations, sometimes you see the notation for sk subset of S, we mean a subset of S with cardinality k. So example, find the number of k combinations of S with cardinality n. So the solution goes like this. So for a k permutation, from last week we know how to compute the k permutation. So for k permutation, each k permutation corresponds to a k combination. This we can call it, later in mathematics, you can call forget map. That means you just forget about some of the structures inside, because A1, A2 to AK as a k permutation, you have the order, but as a k combination, you just forget about the order. So sometimes in some advanced textbook, they call it forget map. And for each k permutation, we can assign it to a k combination. But now we noted that there are many different permutations correspond to the same combination. For example, this, or okay, let's say k a1, a2, ak minus 1, or whatever it, you can rearrange a1 to ak. So sigma 1, a sigma 2, a sigma k. So where sigma is a permutation of 1 to k. They all map to the same combination. Okay, and noted that we have P and K permutations of S, and also we have K factorial K permutation or permutations of 1, 2, 3, 4 all the way to K. Then the number of K combinations just a quotient p n k divided by k factorial. This is because for each k combination correspond to k factorial permutations. Okay, so the number of k combinations should be divided by k factorial. And we introduce another notation. We call this as CNK, means the number of k combinations of n elements. And it's n factorial divided by k factorial n minus k factorial. Okay, and then remark. We introduce some convention. When k is 0, we call it Cn0 or zero combination. And this is, we introduce a notation, parenthesis nk, parenthesis. So this is same as Cnk, but more commonly used in the used as a binomial coefficient, appear in the Newton's formula. And we also call it n choose k for short. Or there's some notation as C superscript k and subscript n is same as C and k. You can always see these notations in other textbook or other journal papers. And then the convention. So n choose k is 0 if k is less than 0 or k is greater than n. And n choose 0 properties. It can be as a consequence of the previous convention that Pn0 is 1. So n choose 0 is 1 because by definition n choose 0 is n factorial divided by n factorial and 0 factorial. And 0 factorial is 1, therefore this is 1. And the Cnn is 1. And the less obvious property is the following. This is, let's give a short proof. This is because n choose k is n factorial divided by k factorial n minus k factorial. n choose n minus k is n factorial divided by n minus k factorial k factorial. Let's be slow. n minus k factorial. So they are saying, or you have a quicker combinatorial interpretation, just like n choose k is same as you choose the complement n minus k elements. So they are one-to-one corresponding to each other. Okay. These are 3 basic properties. And next, we will see a very interesting phenomena. It's called Pascal Triangle. So on this side, let me first write down the triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, blah, blah. And you can continue forever. So the rule is like the left side and the right side are all ones. And then the remaining element can be derived as the sum of the two elements on its shoulders. For example, 2 is 1 plus 1, and 3 is 2 plus 1. 6 is 3 plus 3. So by induction, as soon as you fix left side and the right side, you can figure out all the other elements in between. Okay, so that's called Pascal Triangle. And if you familiar with distribution law of some polynomials, and you will see that is the coefficients. So let's see. So each horizontal line is the coefficient of the corresponding distribution of some linear function, power of some linear function. So for example, x plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay, and now if you have this part, xy is not important. X and y not important. You can use other notation. For example, d plus 1 to the fourth. So d to the fourth plus 4d cubed plus 6z squared plus 4z plus 1. Okay, so the Pascal triangle appear naturally in our previous algebra. Okay, then we are going to prove the phenomena rigorously. Also, I should say just one more common remark. All n choose k appear in the Pascal triangle. So you can find, so all the combinatorial numbers are there. Okay. So we want to prove the remark or equivalently. We want to show that there's another very interesting intrinsic addition formula between combinatorial numbers. That is, n choose k is same as m minus 1 choose k plus m minus 1 choose k minus 1. So I will give two proofs. So first proof, we just do by brute force. If you want to prove the identity, we just subtract left side from the right side from the left side, and we want to show finally we get 0. And we just plug in the formula n minus 1 factorial k factorial n minus k minus 1 factorial minus n minus 1 factorial k minus 1 factorial n minus k factorial. And we uniform the denominator, choose k factorial n minus k factorial. And for the numerator we have n factorial minus n minus k times n minus 1 factorial and minus k times n minus 1 factorial. And therefore, for the last two terms, you figured out n minus 1 factorial. You have n minus k plus k, which is n. Therefore, you finally have 0. The identity is established. Okay, now let's look at the second proof, which gives you some combinatorial interpretation of the phenomena. So we first noted that n choose k is same as the set of the number of all k subset of 1 to n. So we consider the set of all k subsets of S, where S is 1 to n. And noted that each element, each k subset, either contains 1 or doesn't contain 1. So we can split the whole set into two parts. So one is with 1. So we have set of all k subsets of S with the form 1 A1 AK minus 1. And if it's without 1, then we have the set of k subsets of S with the form A1 to AK contains in 2, 3, n, because you don't have 1. And also, the number, the cardinality of this set is nk, n choose k. Now let's compute the cardinality of, so for the cardinality of this set, it's easy to see just n minus 1 choose k, because now the set is 2 to n. You only have n minus 1 element. Therefore, we need to figure out what is the cardinality of this subset. So note that there's a bijection between the elements in this set with the following set of k minus 1 subsets of 2 to n. Just like you truncated A1 to AK minus 1. Because you always have 1, so just forget about 1. Delete 1 from each k subset or each k combination. Then you have a k minus 1 combination, and the remaining elements are chosen from 2 to n. Therefore, the number is n minus 1 choose k minus 1. And then you have the summation. Because here, the total set is a union of the subset on the left and the subset on the right. Okay, and then we introduce another very interesting formula. for integer n greater than later on when we learn generating functions, we probably you will see it's easier to do this. Or when we know the Newton's binomial formula, it's more or less obvious. Okay, so I will give 2 proofs or 3 proofs. So first, by induction. So in combinatorics, induction method is very important, and that also the thinking process we usually go through. For general situation, when n is arbitrary, we don't know how to do that, but at least we can try some small numbers. For example, I haven't write down the formula. Never mind. For example, when n equals 1, 0, even 0, 1, 2, 3, as soon as you figure out small numbers, probably you will find the pattern, and then do induction, you will get through the whole proof. Okay. The thing we want to prove is n choose 0 plus n choose 1 all the way to n choose n minus 1 plus n choose n is 2 to n's power. This is what we want to prove. Okay, and when n is 1, then we have 1 choose 0 plus 1 choose 1. And by definition, this is 2, so it's 2 to first power. And now suppose star holds for n equals k when n is k plus 1. That's the usual induction process. You assume it holds for n equals k, and you go to prove the case when you increase n by 1. Okay, then you need to compute the following quantity: n plus 1 to n plus n plus 1 to n plus 1. Okay, since we want to reduce the formula to here's k, sorry. Since we want to prove the case when we only have k, then we need to reduce k plus 1 choose m to some form like k choose m1 or k choose m2. Okay, and then the natural way is we use the previous formula here. Notice that here, although right side is a little bit more complicated than the left hand side, but they have a common feature that n is reduced to n minus 1. Okay, then here, use that formula. Then you can write down as k plus 1 choose 0 is k choose 0 plus k choose negative 1. And then k plus 1 choose 1 is k choose 1 plus k choose 0 all the way down to k choose m plus k choose m plus 1 plus all the way down to k choose k plus 1 plus k choose k. Okay, then let's do the following. Notice that each big bracket you have 2 terms, And now we want to reorganize them, rearrange them. So we have two lines. The first line, you just choose the combinatorial numbers with smaller lower subscripts. So we choose this one, this one, this one, this one. So write as, okay. So k choose -1 plus k choose 0 plus k choose 1 plus all the way to k choose m-1 plus all the way to k choose k-1 plus k choose k. And then we choose the remaining items in each parenthesis. So you have k choose 0 plus k choose 1 plus k choose 2 plus all the way to k choose m plus all the way to k choose k plus k choose k plus 1. Okay, then noted that k choose -1 is 0, k choose k plus 1 is also 0. And then what do you have? You have that this is just 2n, 2 to k's power by induction. And oh, sorry, I don't use this. The second part is also 2 to k's power. So finally, you have 2 to k plus 1's power. Then we finish the induction. Okay, and now let's look at the second proof, which is a combinatorial interpretation. So on the left-hand side, we consider the set of all subsets of 1, 2, 3, all the way to n. And the right-hand side, we just divide the left-hand side into the following subsets. So 0 subsets and 1 subset, 2 subsets, k subsets, n subsets. Noted that the left-hand side is a disjoint union of the right-hand side. And if you compute the cardinality of each set, so for left-hand side, we already compute that the cardinality is 2n. And then the right-hand side, so this is n choose 0. This is n choose 1, n choose 2, n choose k, and n choose n. Therefore, the cardinality of left-hand side, because it's a disjoint union, so the left-hand side, the cardinality of left-hand side should be the summation of cardinalities of the right-hand side. Okay. And the third proof, actually, if you know the Newton's binomial formula, so x plus 1 to n's power is x to n's power plus n choose 1 xn minus 1 times 1 plus n choose 2 xn minus 2 times 1 square plus all the way to n choose n minus 1 times k times x times 1 to n minus 1 plus n choose n times x0 times 1 to n's power. And then let x equals 1. Then we left hand side we have 2 to n's power. Right hand side we have n0 plus n choose 1 plus all the way to n choose n. Newton binomial formula. Okay, next let's look at some other example. So consider some real problem. Consider 4 by 6 grid of city streets. How many ways one have to go in 10 steps, each north or east from A to B. So the problem is like 2, 3, 4. 1, 2, 3, 4, 5, 6. So that's a grid, and A is here, B is here. We want to know how many ways are there. We can go from A to B, and each time you go either north or east. That means you cannot turn back. It's always to the direction of B. Okay, and as we did for all the previous problems, when you have a real problem, we need to connect it with some combinatorial models, or in other words, you need to construct some bijection from the real situation to some model involving permutation, factorials, or combinations. Any non-combinatorial results. So here, left-hand side, we have paths according to the problem. That means you go east or north only. And then we claim that there's a bijection from each path to sequences E n with 6E and 4n. This is easy. Just no matter where you go, you just the only thing important is the direction. So you just keep note the direction. So for example, for this path, you go east first, and then north, then east, north, east, north. Totally, no matter how you arrange, any path will consist of 6E and 4n. And for each different sequence, it corresponds to a different path. So this is a bijection. And now we can further simplify. This set is already simpler than the previous diagram. because that is 2D. This is just a sequence. But we want more. Because you have 10 positions and only have E and M. So to decide such sequence is the same as choose 4 position to fill in N. So that is 10 choose 4. And for 10 choose 4, this is easy. So is C10 4 or 10 choose 4. Okay, next let's talk about the permutation of multisets. In different textbooks, they may have different notation, and I think most books they don't use multisets. The notion of multisets, but it's all. I think the author here thinks multisets is easier when we have only finite sets. If you have infinite sets, then the multisets probably will be problematic. You cannot define such thing. Okay, it's very complicated. Set theory is very complicated. It's very easy to construct some paradox. Just like you cannot say a set contains everything. Okay. Or you have the Rossel paradox, all kinds of paradox. And the mathematicians usually work in some well-controlled sets, just like Tamero axioms and the Tamero axioms, or CFC axioms. Then we are much safer. And in combinatorics, usually we don't need to worry too much about that because all things we have eventually is finite. We never do something infinite. Although the method might be infinite, involving infinity, but the result is always finite. Otherwise, the computer cannot test. Okay, and here a multiset M is a set S together with a function R from S to infinity. Oh, so that's called multiplicity. Where R is a repetition number of X. Okay, and then by the cardinality or size of M, we mean the summation of all the repetition numbers. Or if you don't like this notation, that's okay. You can use your own way to describe your problem. But later on, if you're familiar with this, probably when you're writing down the answer by yourself or state the problem, it's easier. While if you write your own paper, it's better to use a convention used in that field. Probably in your field, there's a conventional way to state such thing. If you introduce a new convention, you should state it clear to your colleagues. So definition. Eventually we want to consider the permutation. So here, let's define what is a permutation of a multiset. If S is a multiset, an R permutation of S is an ordered arrangement of R of the objects of S, or R objects of S. So if cardinality of S is n, then an n permutation of S will also be called a permutation of S. So notation is similar. And now let's look at some example. So first example. So here's the way we usually denote multiset. We don't write down the repetition function or repetition numbers independently. We just included that in the definition of S. So 2 times A means, okay, so I will first write down notation and then this is a problematic way to write down the actual meaning, because when you talk about set, 3C should be the same as A, B, C as a set. But when we talk about multiset, we still conclude the multiplicity. So that means you have 3 elements, A. But maybe you can use some subscript to distinguish them. So A star, A delta, A square, B star, B delta, C star, C delta, C square, such that they don't collapse after you're taking the set. Or according to the definition, you have the function Ra is 2, Rb is 1, Rc is 3. Okay. So all I want to say is, please have some own interpretation of this multiset instead of just remembering the formal language. Okay, now what is 4 permutations of S? That means you need to take 4 elements out of the multiset S, and then there are many, but we can give some examples. For example, you can have A, C, A, C, A, B, C, B, C, blah, blah. You have lots more. And permutations, then you need to include everything. Sorry. You only have 2A here. Permutations, there will be A, B, C, and then A, B, A, C. You can change the positions. And the previous, one more example, let's see. Previous sequences of n and e with 6e for n. So that is that are actually all the permutations of the set 6e, 6 times e, 4 times n. Actually, we already made that before. Also, there are another simple example we talk about all the time. That is when all the multiplicity is 1. So this turn back to the original set. And then the number of k permutations of S is P is N and K. Okay, and then the natural question is how to compute the number of k permutations. So the easiest case when the multiplicity is infinity. So let S be a multiset with objects of k different types, where each object has an infinite repetition number. Then the number of R permutations of S is k to R's power. So this is because we first write the multiset in the following way. And then you have R positions this R can be arbitrary, can be larger than k or even way much larger than k. And those are positions. And then you need to put in elements, and A1 is an element from 1 to k. A2 is the same. Because the total element is, each type has infinite repetition. So no matter what you choose for the previous A, AR can be choose still from 1 to k. So you have k choices each time. Later on, we will see that when the repetition number is not infinity, then there might be some restriction, and even very complicated restriction on the later choices, for the later choices, k choices. So totally you have k to R's power. Okay, and another example we can consider easily is form permutation. That is, suppose S is a multiset consisting of n1 times 1, n2 times 2, nk times k, and let the cardinality, denote the cardinality of S by n, then by definition this is n1 plus n2 plus all the way to nk. Then the number permutations of S is n factorial divided by n1 factorial, n2 factorial, nk factorial. Okay, now let's prove this. So step 1, let's place ones. That is, you have n positions and you need to choose n1 positions so that you can put in 1. For example, you choose this one, you put in 1, and choose this one, put in 1, blah blah blah. And if some position you are not choosing, then you just leave it as blank. And how many ways you have, then this is n, choose n1. And step 2, let's place 2's. That is, now the configuration you have is n positions, but some are occupied by 1's. Okay, and your job is choose positions for 2's from the remaining blank positions. And note that no matter how you choose positions for 1, now you have n minus n1 blank positions for 2. Okay, so you are choosing n2 from n minus n1. And similarly, you can continue this process, and at step k, the last step, we want to place k's. And then you noted that you have n minus n1 minus nk minus 1. Choose nk. Actually, this is just nk, choose nk, which is 1. From combinatorial way, as soon as you have chosen 1 to k minus 1, then the remaining positions must be taken by k, so you don't have any other choice. Okay, anyhow, if we do product by the multiplication principle, if you have some experiment divided into steps, and each step you have equal number of choices, then the total number of choices is a multiplication, is a product. So you need to do the product, and then we plug in the formula for combinatorial numbers. Because we're not satisfied with this formula yet, we need to simplify it. Okay, and if you write down it carefully, you will see there are obvious cancellations. Okay, and then the cancellations is between m minus n1 factorial, m minus n1 minus n2 factorial, and m minus n1 minus n2 minus n3. Finally, you have m minus n1 minus up to nk minus 1. And then the last one, this is 0 factorial, which is 1. So after all, you have n factorial divided by n1 factorial times n2 factorial all the way to nk factorial. Okay, yeah, I will stop here. Next time we will continue the computation of the numbers of k permutations or multiset, and also discuss the probability. Okay, thanks.